Hello everyone, my name is Tom Burgert and I'm a PhD researcher at Bielefeld in the Technical University of Berlin. In this video, I will present our work titled Rank-Based Geographical Regularization, Revisiting Contrastive Self-Supervised Learning for Multispectral Remote Sensing Imagery. This is joint work with Leonhard Hackel, Paulo Rota and Begum Demir. Remote sensing multispectral images differ fundamentally from natural images due to spatial, spectral and temporal variability. At the same time, they come with zero-cost metadata, like acquisition time and geographical location, which offer strong potential for representation learning without explicit supervision. In this work, we make two main contributions. First, we introduce GeoRank, a rank-based geographical regularization that integrates geolocation as a weak supervision into contrastive self-supervised learning, explicitly accounting for Earth's spherical structure. Second, we systematically revisit core design choices in SSL for remote sensing. Revisit data augmentation, dataset size, image size, and temporal views, and show that several common assumptions from computer vision do not hold in remote sensing. Recent state-of-the-art contrastive SSL methods integrate geographical metadata by adding an auxiliary projection head to WACV2 that predicts cluster assignment of image geolocations. These clusters are pre-computed using k-means and GPS coordinates. However, this design comes with three key limitations. First, it relies on a two-stage procedure with pre-computed clusters. Second, it uses Euclidean distances which poorly approximate Earth's spherical geometry. And third, it discretizes spatial continuity, ignoring fine-grained and mid-range geographical relationships. To overcome these limitations, we propose GeoRank. GeoRank is compatible with any contrastive SSL backbone, such as MoCo, Biol, or Dino, and operates directly on the learned representation space as an additional regularization term. To integrate geographical information, we use spherical distances from GPS locations using the hover sign distance. This guarantees that the geographical information is aligned with the true geometry of the Earth. For each batch, we compute all pairwise distances in two spaces, the representation space of the contrastive SSL backbone and the geographical space defined by latitude and longitude. This gives us two distant matrices that describe how samples relate to each other semantically and geographically. Instead of matching absolute distances between the two matrices, we align the ranks of distances in both spaces. Representation space distances tend to become uniform, while geographical distances are highly non-uniform due to imbalanced geographical distributions. Using ranks instead of absolute distances avoids such distribution mismatches. Finally, we restrict the loss to geographically nearby samples using the radius parameter m and ignore very distant pairs. This reflects the intuition that the relative ordering matters most locally, while faraway locations provide little useful guidance. The final GeoRank loss simply weights the standard SSL loss with the proposed geographical regularization term. We conduct experiments on 7 downstream tasks covering single-label classification, multi-label classification, and semantic segmentation across diverse regions and label spaces that include multiple geographical train test splits. For evaluation, we use macro accuracy and macro average precision. Unless stated otherwise, all experiments use a ResNet 18 WACV2 backbone, a KNN evaluation protocol, and geometric augmentations only. In the first experiment, we evaluate GeoRank across all 7 downstream tasks. We compare to a WACV2 baseline, to existing contrastive methods that integrate geographical metadata, such as Tile2Vec and GeoAware, to GeoBasic, a variant that replaces our rank-based loss with a simple MSE loss, and to state-of-the-art reconstruction-based remote sensing SSL methods. Here we see the results for the WACV2 baseline and the 2 existing contrastive methods that integrate geographical metadata. The first thing that we observe is that GeoRank consistently outperforms or matches existing methods that integrate geographical metadata. Compared to GeoAware of Ayush et al., we observe the strongest gains in datasets like Ben v2, Eurosat v2, and Cashew Plant. Second, the rank-based formulation matters. GeoRank consistently improves over GeoBasic, which uses a simple MSE loss on distances. This shows that preserving relative geographical ordering is more effective than enforcing absolute alignment in feature space. Third, GeoRank also outperforms state-of-the-art reconstruction-based methods when the train test split of the downstream task is geographically related. When downstream splits are spatially disjoint, as we see it for the dataset S4A tiles, this advantage disappears. Nonetheless, this observation is expected, since geographical regularization is only informative when spatial proximity carries semantic meaning. Next, we test whether GeoRank generalizes beyond WACV2. We plug it into SimClear, Biol, SimSiam, and Dino and observe consistent improvements across all methods and datasets. Notably, weaker baselines like SimSiam benefit the most, while even strong methods such as Dino still show measurable gains, indicating that GeoRank is agnostic to the underlying contrastive backbone. We also qualitatively test whether GeoRank behaves as intended. To do this, we visualize t-SNE projections of the penultimate layer colored by latitude and compare GeoRank to the WACV2 baseline. As you can see, GeoRank induces a smooth spatial ordering, whereas the baseline shows no clear geographical structure. We now move to the additional experiments that revisit core design choices in remote sensing SSL. Many contrastive SSL methods for multispectral remote sensing directly adopt the standard data augmentation pipeline from computer vision. In this experiment, we compare the standard computer vision augmentation pipeline to a simple geometric baseline, which avoids channel-based transformations and focuses on spatial invariances. When we evaluate with the KNN protocol, the difference becomes very clear. The standard computer vision augmentations are suboptimal. The geographic augmentation pipeline improves performance by margins between 5 to 20%. With fine-tuning, this effect becomes much less pronounced, because additional optimization can compensate for weaker representations. The results suggest that channel-suppressing augmentations that are useful in computer vision can actually destroy critical spectral information in multispectral remote sensing and lead to a decrease in performance. Previous work on multispectral remote sensing SSL either tested only two pre-training sizes or relied on imprecise experimental setups, such as mismatched pre-processing levels between pre-training and downstream data. In the third experiment, we systematically varied the pre-training dataset size from 10,000 to 250,000 samples. Across pre-training datasets, we observed that downstream performance saturates around 100,000 pre-training samples. Beyond this point, adding more images to the pre-training does not yield consistent gain. A likely explanation is that, unlike computer vision images, remote sensing data has bounded diversity. It is constrained by the sensor characteristics and by the Earth's surface itself, which limits the amount of new visual information additional samples can provide. Due to time constraints, I will only briefly summarize the remaining two experiments. For further details, we refer to the original paper. Previous work suggests that temporal views universally improve contrastive SSL in remote sensing, but we show that this conclusion depends on the setup and that their effect is strongly task-dependent. Finally, we look at the role of input image size during pre-training. Existing multispectral remote sensing pre-training datasets assume that larger input image sizes are universally beneficial, following conventions from computer vision. We show that this assumption does not always hold. Because sensor resolution is fixed in the pre-training datasets, larger image sizes increase spatial coverage, but not the image resolution itself. We find that pre-training with smaller input image sizes achieves similar downstream performance while being about 3 times more efficient. To summarize, we draw 5 main conclusions. First, GeoRank consistently outperforms existing contrastive methods that integrate geographical metadata and improves a wide range of contrastive SSL backbones. Second, standard computer vision augmentations are suboptimal for multispectral remote sensing. Simple geographic augmentations work better. Third, for multispectral datasets, downstream performance already saturates at 100,000 pre-training samples. Fourth, temporal views are not universally beneficial. Their effect is clearly task-dependent. And finally, smaller pre-training image crops retain performance, while enabling up to 3 times faster training. A central limitation of GeoRank, as well as other methods that integrate geographical metadata, is that they provide limited benefit under strong geographical domain shift, where train and test regions do not overlap. Thank you so much for your attention. Please feel free to reach out by email if you have any further questions.